My name is Aleksandr, and today I'm going to share some of the recent progress in my research related to tuning the size of AU nanoparticles and application for the perovskite solar cells. So the plasmonic nanoparticles are some certain particles that exceed nano size, and it's made of various materials that exhibit surface plasmons. Surface plasmons are the coherent, delocalized electron oscillations. It is related to the higher concentration of the electrons near the surface in some certain materials that oscillate. And plasmon nanoparticles, they exhibit some certain properties when they interact with electromagnetic radiation. Among the effects of the interaction is the photothermal effect, which is a local heat generation. The enhanced electric field, which is local field enhancement, because the photon excites the electron to oscillate stronger, so the electrical field is enhanced. And the hot electron injection, so the electron can actually leave the premises of the nanoparticle and could go to some direction. And among the applications of the plasmon nanoparticles are plasmonic antenna, photothermal materials, sensors, and there are some applications in the cancer therapy. Plasmon nanoparticles could be made of various materials, but the main requirement is the high concentration of the electrons, which is the property of metals for the most part of it, and also some certain semiconductor crystals, which have a very high electron concentration. Nanoparticles are in the spotlight of this area because, as I already mentioned, the higher electron concentration is on the surface, and nanoparticles exhibit the highest surface area to volume ratio. So the plasmonic effect are like the strongest for the smaller size of nanoparticles. There currently exist some very many synthesis methods for plasmonic nanoparticles. Among the most popular ones are chemical, wet chemistry, electrochemical, vacuum plasma. Most of these methods, they have their own drawbacks related to a tremendous amount of waste for the wet chemistry, some complexity, scalability, wastes again, scalability, and the price for vacuum plasma synthesis. Price issue related to the more expensive vacuum equipment. So in my work, the motivation is that lack of scalable synthesis methods and the already mentioned drawbacks motivated me to develop better, greener plasmonic nanoparticle synthesis method, and the objective is to optimize the morphology of the gold nanoparticles and apply the developed nanoparticles for the perovskite solar cells. Here is so in my work I mostly work with dry plasma reduction synthesis. This is the atmospheric plasma synthesis, so there is no need for a vacuum equipment. The typical synthesis procedure proceeds as shown on this slide. So it starts with precursor. The metal salt is dissolved in any sort of solvent. For the purpose of this experiment, for example, I used ethanol, and then the precursor in the liquid form is drop casted on the substrate. For the purpose of this experiment, it was FTO and titanium dioxide film deposited on FTO. After that, there is a drying step where precursor, the substrate, is moved to the oven at 70 degrees for 15 minutes, where the solvent is allowed to evaporate to obtain the metal salt in a solid form on the surface, and then it is subjected by plasma. In our laboratory, due to safety, the argon is widely used because it is inert and it is absolutely safe to use. Plasma power is tunable. This is just an example of the plasma power, and treatment time was set to 15 minutes. This is the optimized value. So during plasma treatment, the metal salt turns into the metallic nanoparticles. This is just as can be seen on the skin. And here are the actual photographs of my samples after the plasma synthesis. You may see some brownish tint of the palladium glass and some reddish or pinkish tint of the gold-based. So the observed change of color is the indication of the successful reduction of the salt, because before the reduction there was basically no change in color. It was transparent. Right after the synthesis, so the optical confirmation is usually not enough. So right after the synthesis, the samples were sent to XPS facility, where the XPS spectrum of the AU4F4 level was recorded. We can see two Gaussian peaks in the 4F region, which represents, and due to the location of these peaks, they can be assigned to the metallic gold, which is AU0. So this confirms the successful reduction of the AU salt to a metallic AU. As additional proof, I also recorded the valence band spectrum of the same thing. As a reference, there was a titanium dioxide without nanoparticles, and my sample is the AuTiO2, so gold nanoparticles on the surface of titanium dioxide. You can see that there is some certain tail in the area approaching the Fermi level, which is 0. The appearance of certain tail. This tail is the characteristic of the metallic gold, so it passes 0 during even the calibration, because the XPS is usually calibrated with the sputtered gold samples. So this is the additional proof that gold has been reduced completely. Next, the samples were moved to the powder was stretched off the samples, the titanium dioxide and with gold, or titanium dioxide with palladium. This is just another experiment that proves that with this method, various nanoparticles can be synthesized. It's just focus of this work is gold, but actually, like as a side experiment, I have also successfully synthesized the palladium nanoparticles on the surface of titanium dioxide. So here are STEM images of the gold titanium dioxide powder and the palladium titanium dioxide powder. From STEM images, the average morphology, population, and the average diameter of the nanoparticles were obtained. And using high-resolution time analysis, the titanium dioxide nanoparticles, gold nanoparticles, and palladium nanoparticles, respectively, were identified using the lattice fringes, which were obtained from the high-resolution time images. Here are some of the average particle size. All right, so the next step of my experiment was the issue of how to tune the size of nanoparticles, because for a proper application of the material, it is very important to obtain the desired morphology, not the morphology that we have. So during the plasma synthesis, there are several things that could be adjusted. For example, the nucleation and particle growth rates, they can be adjusted by changing the plasma power. That was a result of my previous research, and in my current work, I have investigated the effect of change of pH on the pH of the precursor solution on the resulting morphology. And then I have came to the certain trend. Here are STEM images of the titanium dioxide gold nanopowder. That was synthesized from the precursor solutions of different pH concentrations. So you could see that the particle size is actually like increasing noticeably through the increase of pH. Here are some results of the analysis. So this is the result of I'm sharing the result of my previous work, that the main finding was that effect of plasma power that decrease, we can, by adjusting plasma power from 200 watt to 100 watt or vice versa, we can change the particle size on about 2.5 times. In this way, the highest plasma power leads to the smallest particle size, whilst the small plasma power leads to the higher average particle size. And as the effect of the pH, the main finding of this work you can see here. So the average particle size is increasing as the pH increases. That actually extends our window of how we can control the morphology, in particular the average size of nanoparticles. So it is additionally the originally synthesized particle were about like 6.5 nanometer average size, and the biggest nanoparticles were synthesized in about 8 at the pH of 8, which were about like 13, 14 nanometers average size. So the size could be the window could be increased for additional 2 times. So to sum it up, the particles adjusting the plasma conditions and the pH of the solution gold nanoparticles could be synthesized in the range of between 5 and 30 nanometers range. Now, moving to the application, as I already mentioned, there are certain phenomena that occur for plasmonic nanoparticles when they interact with light, which are photothermal, enhancement of electrical field, and hot electron injection. So photothermal is out of my interest in current work, and for application in perovskite solar cells, I'm mainly focused on the enhancement of the electrical field and hot electron injection. So the methodology was like simply deposit gold nanoparticles on the titanium dioxide covered FTO glass, and then perovskite is deposited and whole conductor over it, and concluded with the AU contacts. So the addition of the gold nanoparticle is expected to improve the light absorption, injection of the hot electrons, and reduce recombination due to improved local electrical field. So that was the motivation for the application of gold nanoparticles in perovskite solar cells. However, since I was able to tune the size, there are some. Now I have a choice of average diameter of the nanoparticle. Which one should I choose? So basically, on the results of previous works, the Plasmon resonance wavelengths of the gold nanoparticles shifts towards shorter wavelength spectrum as the nanoparticle size decreases. And here you can see the absorption, transmission, reflectance spectra of the methyl ammonium lead iodide material, perovskite. This is the most popular perovskite materials up to these days. So the main point of my work here is to, if you can see here, the black spectra is a reflection spectrum. Yeah, reflection. So you can see there's a certain reflection band here in between 500 and 600 nanometers. And I believe if I add the gold nanoparticles, which absorb light in this wave, in this range of the spectrum, I could get some improvement of the efficiency of the perovskite solar cell. So that was the idea behind, and that's why this band matches well with the smallest nanoparticles, which are 5 nanometer. And this, using the just synthesis protocol, I was able to synthesize these particles. Therefore, the particles I have used only these particles during the manufacturing of the perovskite solar cells. Here is the typical procedure of manufacturing of the perovskite solar cells. So first, compact layer deposition, which is titanium dioxide. Then the aforementioned plasma synthesis, so gold AU nanoparticles of 5 nanometer average diameter are synthesized in the plasma beam. Then mesoporous titanium dioxide layer is deposited using spin coating. Then the perovskite is methyl ammonium lead iodide perovskite is deposited using two-step spin coating. After that, the sample is annealed for 2 minutes to obtain the thick perovskite film. After that, the whole transporting layer, which is spirometad, is deposited using spin coating, and it is concluded with top contact deposition, where metallic gold is evaporated on the top of the perovskite solar cells, and there was a mask. And here you can see the mask that was used during the evaporation and the images of the as-made perovskite solar cells. So about the results, there was some certain issue to the optimization of the concentration of the gold, how much of the gold precursor I should add, because the coverage of gold nanoparticles around the titanium dioxide film changes dramatically as the concentration of the precursor changes. So here are the spectra of as-made perovskite solar cell, including reference and plasmonic nanoparticles in it. So here are some detailed characterizations as we change. So 0 is a reference cell in every spectra. So we observed the increase of the open circuit voltage, a certain increase of the open circuit voltage if we use the gold nanoparticles concentration of around 0.5 and 1 millimole. And actually the current, it repeats very similar trend to that which was observed in open circuit voltage, and these are the expected outcomes. Unfortunately, the magnitude of the increasement is not as much as we expected, but it still cannot be ignored. And as for the fill factor, it actually decreases regarding, like it keeps decreasing upon adding even small amounts of the gold nanoparticle concentration. It is always lower than it is for the reference cell. So as the result, this is the detailed graph which summarizes the efficiency changes depending on the concentration of the gold nanoparticle precursor during the synthesis. So to analyze these results here, this table actually it summarizes the average results of the cells using of the reference cell and the cells using various concentration of the gold nanoparticle, as you can see here. So we can see some certain trend. The short circuit current is increasing, and the maximum was obtained for gold, which was synthesized using half millimole concentration of the precursor, and the efficiency, the overall efficiency was slightly higher, 0.5% higher than for the current conversion efficiency for the reference cell. And the expected increase of the efficiency is much superior than this. Unfortunately, we did not see such a tremendous increase as expected. And the apparent reasons for this lies behind the decrease in fill factor, and decrease in fill factor is related to the unfavorable position of the Fermi level of gold nanoparticle. The work function is around minus 5.1 electron volt, so it is way too close to the hole level in the methylammonium lead iodide. So during photoexcitation and the charge separation, the photoexcited hole could easily recombine with the electron in gold. So I believe this is the main cause for the reduction in the fill factor. And as for the why did the current in high concentration of gold has decreased? Because we expected the increase of the current for any, like, regardless of the concentration. And the problem was that such high concentration of the gold nanoparticle actually reduces the transmission spectrum of the titanium dioxide film plus gold nanoparticles, and that leads to the lower amount of light reaching the perovskite. So lower amount of light, lower the current. Considering all of these findings, the next future perspective direction for the plasmonic perovskite solar cells is use of the materials with a more favorable position of the work function to prevent the recombination between hole from lead iodide, methylammonium lead iodide, and plasmonic material. And additionally, the adjustment of the wavelengths of the local surface plasmonic resonance could lead to another tremendous increase. For example, in titanium dioxide, the reflectance spectrum peaks at around 400, a little bit lower than 400 nanometers. So here I compiled the list of the future perspective plasmonic materials that could be used to make a plasmonic perovskite solar cell, and with expected improvement of more significant improvement of the overall efficiency of perovskite solar cell. So in the conclusions, the green method of synthesis of nanoparticles has been developed. The tools to tune size of the nanoparticles have been investigated to some extent, and then the effect of the introduction of the plasmonic nanoparticles on perovskite solar cells has been studied as well, and based on that, the future directions are proposed. Thank you for your attention.